Welcome to this lecture on introduction to 60 SRAM cell and the issues that one finds with 60 SRAM cells in near threshold voltage operation. So, this is part of module 5. First we will discuss memory hierarchy, then we will discuss how 60 SRAM cells operate, their read operation, their write operation, and sizing issues, and also issues with 60 SRAM cell when using in near threshold voltage operation. So, we might be aware the highest hierarchy of memories is the so called L0 level 0. So, here these are registers which are to be available most accessible in a very fast manner. You should be able to retrieve data and store data in a very fast manner. And then L1 cache, which is again SRAM. So, from L1 cache the data goes to registers, and from registers it goes to our combinational circuits, data paths or control paths. And then you have L2 cache. So, here you store data which is required for the processing, so instructions, etc. And then you have the main memory, which is mostly external to our chip, and it is a DRAM memory. So, that is also relatively fast, relatively easily available with smaller access times to your processor, and it acts as a interface between the disk memory and the processor. Then you have the disk memory, and here it is within your computer, and here you store all the data, etc., which you need to retrieve for operation, which you may need to retrieve for operation. It is relatively quite slow to access data from the secondary memory. This is not semiconductor memory typically. And then you have the remote data available on other servers or from which you retrieve from say cloud, etc. So, the SRAM is memory which is closest to the processing unit. So, it is either in the forms of cache memory or even registers or SRAMs of some kind. So, it is most easily available memory, and it should be robust, the data should not change, it should be predictable, and it should have a very fast access time. You should be able to read the data very fast and also write it fast enough. So, that is and it should not be high power consuming, because it is on chip, you do not want it to be consuming large amounts of power. So, how does it work? It is a cross coupled inverter pair essentially which stores the data, and there are these access transistors, and bit line and bit line bar store the data, and these give access to the data stored in this cross coupled inverter pair, and to either write or read operation, which we will discuss later. So, what is the basic principle of storing the data in this cross coupled inverter pair? So, if you plot the voltage values of Q and QB, these are not logic values, but voltage values through inverter M1, M2, M1, M3 and M5, M4. So, if we look at the inverter M4, M5, then this is Q is the input and Q bar is the output. So, it would look like this. And for inverter M1, so this is M4, M5. For inverter M1, M3, the characteristic would, because there the input is QB and output is Q, and the inverters are matched. Suppose the inverters are matched. So, this is for inverter M1, M3. Now, there are two stable points and one unstable point or metastable point. So, at these stable points, the cross coupled inverter pair is in a low loop gain state. So, any noise or disturbance in voltage on any of the nodes Q and QB would tend not to disturb the state of the back to back connected inverter pair. Back to back connected. Okay. So, however, if we look at this metastable point, if the voltages of Q and QB are at this level, then both M1 M3 and M4 M5 in high gain are in high gain state here, isn't it? So, any minor disturbance in the voltage values due to say noise would move the inverter pair from this metastable state to one of the stable states. So, these three states, stable states and the metastable state, are very important in the read and write operation. So, now let us look at the read operation. Here, while you read, the bit line and bit line bar are biased at VDD, set VDD, and this is also at VDD initially. Okay. And then word line is asserted from 0 to VDD. So, what does this do? Now, here you have a 0 stored here and you have VDD charge equivalent to whatever is the node capacitance into VDD stored here. This transistor M1 is therefore, while you read, so since you have a 0 stored here, M4 is on and M1 is off, M6 is off and M3 is on because you have a 0 stored here. So, here the equivalent circuit is for storing 0 here and VDD here. Because you have a VDD stored on QB, M1 is on. So, first let us see the case where a 0 is stored on Q and for QB it is obviously VDD. So, in that case Q4 is M6 is on and M1 is on, and therefore, while reading you would observe that here there is no change in voltage because both are at VDD, and here there is a little change in voltage. This writes into this, but the transistor is biased at a high gate voltage, whereas Q5 would see a gate to source voltage which is relatively small, because this would carry current only if its VDS is non-zero. So, therefore, this would come to a voltage delta V which is larger than 0. So, VGS of Q5 would be VDD minus delta V, which is smaller than the VGS of Q1, which is VDD itself initially. So, therefore, you would find that Q5 needs to be more stronger than Q1 to carry the same current. But Q1 is in linear regime because its drain voltage is relatively quite small, whereas Q5 operates in saturation regime because its drain and gate voltage are almost equal. So, now this current discharges BLB from VDD a little, and this difference in BL and BLB, how much should it discharge? It discharges till the pulse width of the word line. So, which we can see here. So, this we can call word line's pulse width. So, the pulse width of the word line should be such that the discharge is sufficient to flip the sense amplifier. So, there would be a sense amplifier which senses the difference in voltage between BLB and BL and senses that there is a 0 stored in this bit cell. For Q, there is a 0 stored in this bit cell. So, this operation would take a while and delta would be larger if you allow it for a longer time. So, you allow it for such a time, that is the pulse width is such long such that your sense amplifier is able to sense. So, now if delta V is larger, then the bit line discharge is larger and therefore, you will have a larger power consumption but the sense amplifiers would be simple and you will have smaller power consumption in the sense amplifiers in that sense. So, that is why it is an optimization with how much should be the delta which you keep. So, if we look at read operation where Q is VDD and QB is 0, you would see that it is initially it is M3 which is on and M4 which is on, rest of the transistors are off, and if W4 by L4 divided by W5 by L5 is large. So, what is happening? How much discharge is taking place from BLB is what matters. So, it would depend on this ratio, because if W4 by L4 divided by W5 by L5, if this is large, what would happen? Then this transistor is weaker and this transistor is stronger. So, if it is larger, then there will be a smaller change in voltage delta V here. So, there is a change 0 plus delta V which happens here, and there is a change VDD minus delta V2 which happens here, isn't? So, now this delta would be smaller if W4 by L4 is larger, because M4 would be stronger, it would require a smaller VDS to carry the same current, and that would also increase the VGS of M5 and it would also carry a better larger current. So, you will observe that the read operation takes place faster, you require smaller pulse width, and also there is a lesser disturbance in the voltage values of the cross coupled inverter. So, if you keep W4 by L4 larger as possible, your read operation is more efficient. So, that we can see as you reduce the cell ratio, you find that delta V at this node QB is keeping on increasing. We want it to be as small as possible, so that the cell does not change much from its original state. And so, this is one consideration. So, here you want W5 by L5 to be small. So, this you want this transistor to be small. Now, let us look at the write operation. Okay. So, also let us see what happens if you reduce the supply voltage, that is you come to the near threshold regime. In near threshold regime, the linear current is much smaller compared to saturation current, because the subthreshold linear regime has current given by exponential VGS minus VTH minus lambda VDS by NVT into 1 minus exponential VDS by VT. So, if VDS is very small, which is the delta V here, then this current is exponentially it becomes smaller, and the linear currents are very small in compared to the currents in subthreshold saturation in this regime. So, that is why you would have delta V1 which is relatively larger while reading. While reading it becomes relatively larger, but then that also reduces the VGS of M5, which reduces the current through M5 exponentially. So, to have significant value of current, you would require M5 to be very large. M5 should be very large, and then that would disturb the cell ratio. So, here while reading you have this problem that M5 has to be large to supply significant current, and but that would reduce the cell ratio, and therefore, that would increase delta V1 by a value which can also flip the cell. So, you have issues with the near threshold operation, and these issues must be handled while sizing the cell. Also, the other issue could be that a small mismatch between or variation would change the transistor characteristics drastically. So, whatever design you do may not actually work while reading, because reading is a very sensitive operation. So, and reading through a pass transistor is very difficult, because while you, if this is the source and while you read a 0, it is efficient, but while you, because the pass transistor has its source at 0, so that is efficient, but as we will see while writing you will have problem through a pass transistor. So, the 60 write operation, if we discuss this, so here you have a 0 written here and you have a 1 written here, and you want to write initially you had 0 and 1 and you want to write 1 and 0, you want to write 1 here. Okay. So, now what you will do, you will assert bit line to VDD and bit line bar to 0 and put on the word line. That is the pulse width. So, now this is word line pulse width. So, likewise you have a similar pulse on this side because these are connected. So, now to write you will find that M1 is on initially, M1 is on, M3 is off, M6 is on and M5 is off. So, you should be driving this node 0 to a high value, so that it puts off M6 and puts on M4. So, you require this voltage now to be high. Initially while reading you wanted this not to go very high, you wanted this to be as small as possible, delta V here, but here you want this delta V here to be large. So, W6 by L6 and W5 by L5, if you take the ratio, if you increase this ratio, you find that the delta V is now larger. Since M5 is now weaker, when you increase this ratio, since M5 is weaker, you will find that the reduction in the voltage of this node QB from VDD. So, if you increase this ratio, you would find that there is a larger voltage required to, larger change in this Q, voltage Q from 0 required to put off the transistor M6, or there is a larger change in the value of QB from VDD, so that the inverters flip. So, an increased ratio would require a larger change. So, that we can see from the other, if we look at the transfer characteristics. So, if we increase the ratio of M6, if we increase the size of M6, we would find that the transfer characteristics would move this way. So, the metastable point has moved to a higher value. So, if you want to change the value of QB from 1 to 0, while discharging you must take it close to the metastable point, and that is to be done through the access transistor. So, if you increase the size of the P MOSFET, suppose you have a 0 stored at Q, then you will have to change the metastable value as this. Now, from 0 you will be moving it to a lower value, you will be changing the change in voltage value from 1 would be smaller and from 0 it would be larger. So, from 0 you will have to have a larger delta V, so that the flip happens at the cell. So, you would observe that the delta V at this node increases as you increase this size of M6. So, what would happen if you operate at a near threshold voltage in near threshold voltage regime? Charging this node Q through the pass transistor M2 would be a very inefficient process in near threshold voltage regime, and because you would require, one thing is that the transistor M1, it should not operate in linear regime or subthreshold linear regime, because then the currents would be extremely small. So, it must operate in subthreshold saturation regime, so that the voltage here increases, and but that would reduce the VGS of this. So, the current through M2 it would become exponentially smaller as the value of Q node Q's voltage increases. So, that would need M2 to be quite large. So, these sizing issues would be quite different in near threshold regime, The other issue is, as we had discussed, mismatch or variation between transistors that would make the design very unpredictable. The performance would be highly unpredictable with any design, because a small variability would change the performance significantly. So, we have now discussed the 60 SRAM cell write operation. Now, let us discuss issues, challenges. Now, we will discuss the noise margin in detail in another lecture, but I will give a brief, a very intuitive and very brief kind of idea. So, this is the noise margin signifies static noise margin and read noise margin. These static noise margin, for example, signifies the value of change in the for an inverter, the value or for a back to back connected inverter pair in a memory, it signifies the value that can change, voltage value that can change in on the both the nodes Q and QB, which would lead the memory back to the original static or original hold value. Suppose the original hold value is this light shaded butterfly curve or light shaded voltage transfer characteristic of both the inverters is here in light shade. So, now in this is one of the stable points and this is another stable point, as we know. So, the value of input and output voltage change for an inverter, or the change in VQ and VQB, which can be tolerated, which would again take it back, snap it back to the original state. Either this, suppose the original state was this VQ 0, VQB, VDD, then it should snap it the value or the change, or due to noise or some other reason there is a change in input and output voltages, but it is snapped back, the back to back connected inverter pair is snapped back to the original value. So, whatever is the maximum change that can be tolerated in this way is called static noise margin or hold noise margin. So, in the hold state, when the state VQ, VQB 0, 1 is held, it is in hold state, that is when the access transistors are off, word line is 0, okay, word line is 0. So, for that, what is that maximum value? That is hold noise margin, okay. Now, suppose the word line is being read. So, if the word line is being read, the access transistors are obviously on. So, WL is 1. So, word line is being read. Suppose VQ is supposed to be VDD, VQB is supposed to be 0. But now, since M5 is on, M4 is also on, VQB cannot be 0, because there is some, there would be BLB is VDD, BL is VDD, you are reading, isn't? So, in that case, since M5 and M4 both are on, there is a current through this, and that current would result in this VQ being VQB being somewhat higher than 0. So, maybe 0.2 VDD, okay. It will assume some value, and that disturbance of QB, a little small disturbance of QB will be sensed, the difference between Q and VBL and VBLB, the difference that develops because of this would be sensed by the sense amplifier, and that is how the read operation happens. But here QB will now not be 0 volts, but it will be some higher voltage value. So, now in this state, if there is a noise, then a smaller noise will lead to disturbance of the cell, because this is already at 0.2 volts, 0.2 VDD suppose, and this is at VDD. So, now this is already at a higher voltage. So, a smaller change, a smaller noise at this node would flip the state of the cell. Earlier in the hold state, suppose it was this value of the noise which was flipping the node, then it will be a smaller value which will flip the node now, flip the cell now. So, this is called read disturb. Noise voltage Vn flips the cell in hold state. A noise voltage Vn read, which is smaller than Vns, would flip the cell in read state or during the read operation. So, now what seen is that if one looks at the compares the static noise margin, then the static noise margin, read static noise margin for 0.6 volts and the hold static noise margin at a smaller supply voltage 0.3 volt, they are comparable. How are they comparable? Here this is the probability that the static noise margin has a certain value, the probability that the static noise margin has a certain value. Okay. So, now this could be either hold static noise margin or read static noise margin. The continuous lines are all hold static noise margins and the dashed lines are all read static noise margin. So, hold static noise margin tells us the value of noise voltage which can be tolerated without switching the state in hold state, that is when the access transistors are off, and read static noise margin tells the value of noise voltage which would flip the state of the cell when read operation is being performed or when the BL and BLB are at VDD and M2 and M5 are on. So, one observes that there is variation in these transistors, isn't the variability is there, threshold voltage, mobility, line edge roughness, or several causes of random variability, systematic variability. Ultimately, they would result in threshold voltage and mobility, channel length, supply voltage variations, temperature variations. There are several causes of variations. So, now with those variations, what is the probability that the static noise margin, lot of Monte Carlo simulations were done and using a large number of Monte Carlo simulations, 6 sigma probability was seen. So, what is the by the authors? So, what is the 6 sigma probability that what is the 6 sigma of the Gaussian distribution of static noise margins, both read static noise margin and hold static noise margin. So, what is the 6 sigma probability that the static noise margin would assume a certain value. So, it is suppose it is 0.05 volts, okay, 50 millivolts is the static noise margin. So, 50 millivolts if it is the static noise margin and the VDD that they are targeting is 0.3 volts. So, at 0.3 volts what they find is that the hold static noise margin is equal to the probability is that it will be 50 millivolts is similar to that the probability of read static noise margin at 0.6 volts whatever its value, both of them are similar and have a similar probability at this value. So, now what does this signify? So, this signifies that see the whole read static noise margin at 0.6 volts was something which one could design the cells. It is some value which so you get a read static noise margin at 0.3 volts. So, at 0.3 volts you get a whole static noise margin that is like read static noise margin at 0.6 volts. So, read static noise margin is as if it is you are operating at half the supply voltage and you get the same whole static noise margin. Okay. So, when you reduce the supply voltage, you want to carry on with the whole static noise margin, and at least the whole static noise margin should not have a very small value. And so, how to ensure that? So, to ensure that the idea that is resorted to is that separate out the read and write mechanisms. So, in the hold state and while you are writing, you have a different circuit and for reading you have a different circuit, because to write into the cell you need to disturb the cell. To write into the cell you need to actually disturb the cell, state of the cell, and to disturb the state of the cell you need to have a write noise margin which is small enough. You do not want a very large value to disturb. So, write noise margin is defined in a different way, that is why. So, we will discuss that in another lecture. So, you want it to be disturbed easily, and in hold state you want it to hold. When the access transistors are off, you want the cell to hold its well, and while reading you want it not to be disturbed. Okay. So, fulfill all these conditions simultaneously becomes a difficult task, and as we were seeing earlier, the noise margins at for hold state and for read noise margins, they are similar for when you double the supply voltage. So, when you reduce that supply voltage, if you want the noise margins to be good, then you must separate out the read circuitry, so that your read design considerations. So, for read, the design considerations are more stringent. So, while reading, you want, for example, QB not to be disturbed in the 6T transistors. Suppose this red encircled part is not there, it is just a 6T transistor, then you want QB not to be disturbed much. So, while reading, you want QB, the voltage of QB to be disturbed by a very small value, but in that case there will be very little change in voltage which is developed here. So, if you do not want it to be disturbed much, then you want M4 to be very strong compared to M5, and so in that case what would happen is, while you are holding, then so the sizes of transistors would increase. You will have to follow more stringent conditions for designing, and the circuit will not be very efficient. So, you are, so we will discuss that later. So, you are in more detail. So, the idea that is resorted to is that you separate out the reading mechanism of the circuit. So, how is this done in this 8T SRAM cell? The write and the traditional 6T transistor is for holding and writing, okay, and the read is done through a sensing circuit which comprises traditionally of M7 and M8, these transistors, and read bit line is now separated out. So, when read word line is on, then this M7 is anyway, if QB is VDD, M7 is anyway on, and when read word line is on, there is a little disturbance which is RBL is discharged, and you want to discharge it till the value which the sense amplifier can sense. So, whatever is your sensing circuit for RBL, that determines how much it should get discharged, and accordingly you will fix the pulse width of the read word line. And so, now this 60 part of the memory cell is determined entirely by your static noise margin and write noise margin. So, you want to write efficiently into it, and you want to hold the, when M5 and M2 are off, then you want to hold the state with good robustness, cell stability. So, that is, so you can separate out both the problems. So, this M2 and M5 are on only when you want to write. So, this write word line is asserted and you write into the cell like in a conventional 60 SRAM cell, and when you read, only the read word line is asserted, write word line is 0, and you read through this M8 and M7. So, the read operation is when WL is on, WWL is 0, RWL is VDD, and you read through this sensing circuit. For write operation, as we have discussed, RWL is 0, WWL is 1, and you, for example, if you want to write 1, then you will have WBL as VDD and WBLB as 0, and this would be VDD and this would be VDD. So, that would write into the circuit. If you want to reduce the access time or increase the reliability of writing, you want to ensure that the cell is flipped, then WWL is asserted to a voltage which is higher than VDD. You can, these kind of techniques are also used. Now, we discuss 10T SRAM cell that has been proposed. So, in this again the essential idea is that you separate out the right part of the cell, and this is the right sensing circuit, rest is the traditional 60 SRAM cell. This is the traditional 60 SRAM cell, blue. So, how does this function? Write is just as we had discussed now, and read is different, we will discuss. For read operation, RWL is kept at 1, okay, kept at VDD, and WL is kept at 0. So, when RWL is kept at VDD, as can be seen, suppose QB is 1, M9 and M7, M7 is on, M9 is off, and RWL suppose it is on, then M8 is on, QB is VDD. This would RWL being on would ensure that M10 and M8 are on, M8, M10 are on, and QB being VDD would ensure that M7 is on. Okay. So, what would that result in? That would result in RBL being discharged from VDD through this path. So, RBL being discharged from VDD would signify a QB being 1, that is a 0 being read, 0 being read. Okay. Suppose it is in hold state. If it is in hold state, RWL is 0. So, M8 is off as shown here, M10 is also off, but QB is at VDD suppose. So, M9 is off, M7 is off, on. But what you find is that 2 transistors in stack are off, 2 NMOS transistors. So, though M7 is on, but 2 series transistors are in NMOSFETs are in off state. So, there will be an intermediate voltage here between M10 and M8, there will be an intermediate voltage which is non-zero. So, the VGS of M8 is now negative because RWL is 0. So, in the hold state when QB is 1, RWL is 0. This node between, if we call this node as X, Vx is greater than 0 because you have to have some value of VDS. Suppose this node is Y, since M7 is on, Vy is 0. So, if you have to have some leakage current flowing through M10, it has to have a non-zero VDS and therefore, Vx is larger than 0. So, that will give a negative VGS for M8, VGS of M8 is now smaller than 0. So, you will have an extremely small leakage current. So, that would ensure an extremely small leakage current. This is regarding the hold state when QB is 1. Okay. Suppose QB is 0, then in the hold state it is even better. M8 is 0, M9 is now on because QB is 0. So, Vx is, so when QB is 0, Vx is VDD because M9 is on, Vy is a value which is larger than 0 because again there is a leakage current through M10 and M7 and M7 cannot have a non-zero VDS. So, Vy is larger than 0. So, that would ensure that VGS of M10 is negative, VGS of M8 is also negative, which is equal to minus VDD. So, this would ensure that I leakage is very small. So, this 10T transistor over the 10T SRAM cell over the 8T SRAM cell has the advantage that in hold state it has extremely small leakage. Otherwise, what happens is that the leakage currents start discharging the bit line or bit line bar, and that can cause the leakage currents may cause a false reading operation in the sense amplifier. So, that is to a great extent overcome using this 10T SRAM cell. How is the write operation done in this 10T SRAM cell? The actual power supply. So, all these are the cells, 10T SRAM cells, and all of them share a power supply. The layout is such that the cells along one word line storing so they are all having shared power shared power supply, and this power supply is through this PMOS transistor, a large size PMOS transistor that gives the power supply to all of them, all the 10T SRAM cells. So, when you want to write, the write signal is asserted, and a word line of write that is also put on, and this VDD on bar, this signal is put to 1. So, once this is put to 1, the supply voltage VVDD is 0. This will ensure that VVDD is equal to 0. So, that would make the cells. So, these inverters are now having a 0 supply voltage. So, what happens is, suppose you have VDD stored here and 0 here, you are writing 0, and this is 0 stored here and VDD here. Okay. Because there is no fight from the back to back connected inverter, they are having a 0 supply voltage. So, their P MOSFETs are off, both the P MOSFETs. This P MOSFET is off because its input gate voltage is VDD, and this P MOSFET is off because its gate to source voltage is again 0. So, both are off. So, by pure capacitive charge sharing between the bit line and node Q, it assumes a higher voltage like this, and so QB assumes a higher voltage like this, and Q assumes a 0 volt, and VVDD is floating here as it is floating at 0 at a low voltage. Now, again VVDD is put on, and these two values already stored at Q and QB, they ensure that Q and QB are switched to, because VVDD is now put on. So, already the P MOSFET, this P MOSFET is now, this now turns to a higher voltage, and this has been switched to near 0. So, therefore, this P MOSFET is now on. So, when VVDD is put on and it assumes a higher voltage, since this P MOSFET is on, this will turn to VDD. So, that is what is happening here. So, this is the write operation of this 10T SRAM cell with power supply voltage being put off. Now, putting off power supply voltage has other challenges, like the other cells where you are not writing can also get affected. So, you would have to put off the power supply of the entire column in which you are writing. So, that is what is ensured by this layout method, where they lay out all the cells in such a way that they share this VVDD line along one column. So, in this lecture we discussed the need for 8T and 10T SRAM cells, and we also discussed their read and write operations. Thank you.